Now we're going to leave the pricing models and we're going to look at a different kind of model that can be set up as nonlinear programming. And now we're going to revisit the advertising example that we saw in chapter 4, where we had the exposures we will get by advertising in and we want the exposures for 6 different demographics, and we had like 8 or 9 programs, and the exposure units were given to us in that example. Now we're going to look at the exposure units being generated as a nonlinear function. So if you use a particular demographic group and if you run X number of advertisements, so how many exposures you will get. In the previous case we assumed it was linear. So now what if it is nonlinear? Because if the more you advertise, the exposure units that you will, effective exposure unit you will get will taper off. So what is the effective exposure we will have? And in the same example we are also going to look at a case where we have multiple points. The first example in this chapter that we saw only 2 points, we had a straight line or a curved line. So now we have multiple points, and how do you fit a line through multiple points, and we will be looking at a mean square error method for that. So let's go to the Excel file. Now here we want the parameters of the curve. So we have historical data here. So how many advertisements we run and how many exposures that we actually got. So these are the input cells. Okay. So exposures, how many ads we ran. So we can actually look at what the function will look like. Okay. So here the x-axis is ads, number of ads. Y-axis is exposures, and the chart title is exposures versus number of ads. Okay, so now we want to fit a line, okay, through these points. Okay, so that will closely align with these points. Okay, so that's our purpose here. Okay, so now we're going to assume that that exposure function will look like this. Okay, so this is a function of number of ads we run. N is number of ads. It's going to look like this: A times 1 minus e to the power of minus b n, where a and b are the constants. So we need, so that's what we have to find. So this is our a, okay, and this is b, and we want to find that. Okay, so this is the actual exposures. Now if we use this function, what would the exposure prediction will be? So here remember, this e is a constant, and in Excel it is given by exp function. Okay, so let's give names here. So we have a, okay, times 1 minus exp, the function exp minus b to the multiplied by n. Okay, so a times 1 minus e to the power of, okay, then we need one more parenthesis. Okay, so that is the predicted value. Of course, since these are 0 right now, so you have prediction of 0. Okay, If you look at the difference between the two and square it, so the actual minus what we are predicting from the line, and square that. Okay. Okay. Now we'll take all the squared errors and we want to find the average of squared errors. So that will be mean square error. But what we want is the square root of that. So we start with SQRT, okay, of the average of the squared errors. So we need two parentheses, and this is called root mean square error. Okay. So now we'll name this cell RMSE, root mean square error. Root mean square error. Now this is so our solver problem is to find A and B such that the root mean square error is minimum. So this is our objective cell. Okay, and let's put some starting value and go to solver. That's what we want to minimize. We have two changing cells and there are no constraints here. So go to options and make sure that we have that. Not this is not checked and that is checked. And here are the coefficients. So now we can set up the predicted for all of these different add numbers and then see how that would look. So predicted would be A times 1 minus, see here, that's what we're trying to do, exp of minus B times the number of adds, which is that. And then we need one more right parenthesis. Okay, so if we run no adds, we're going to have no exposures. Then, okay, let's reduce the number of decimal places here to just one. Okay, now we want to plot the predicted in the y-axis and number of adds in the x-axis. So let's plot that, scatter plot like that. Let's put the plot down here. Okay, we don't need that. So x-axis is number of adds, y-axis is exposures, and chart title is exposures versus number of adds. Alright, so as the number of adds increases, the exposures tapers off. You don't get the same rate, and that's more practical. That's more reasonable. You can't assume that it will always increase at the same rate like a linear function would. It will taper off after a certain point. So we have to do this for each and every combination of the TV show where we're going to advertise and the demographic group. So if we develop all of these demand functions or exposure functions in this case, and then we can run the model as a nonlinear programming model to increase or to maximize the total number of exposures, which we will see in the next example.